So if it swells, the new pile will be there. And so this is the new outline of the pile because of this phenomenon. But this is not negative skin friction. It's only referred to negative skin friction when the reverse happens. So when the pile is unplugged due to expansion, so similarly, due to contraction, and the issue is the clay layer. This is a problem of clay layer. So when it contracts, for example, this layer shortens to that point. So it means the pile will be dragged down with it. So we have excessive settlement equivalent to this due to negative skin friction. So that action of dragging, so is negative skin friction when it's dragging the pile along with it and causing more settlement. Okay. So that's it about negative skin friction. So that's the phenomenon we don't want. So how to solve this is you have to embed this in a stable substratum. In sand, if you don't have sand, you have to embed the pile in material that is clay, that is more stiff, more stable. That the idea of expansion and contraction won't affect the pile. Okay, and so this is a combination of ideas from what we've talked about so far. So we can have clay fill over granular soil, as shown in this figure, and so this is how to calculate the friction, the interparticular friction, the earth pressure coefficients, and so on. But here is how to calculate the downward drag. So if you wanted to find out the negative skin friction, so to speak, what value it is, Qn. So this is a way to be able to do that calculation. So um, and this is a way to be able to do that calculation. Okay. And it's also possible that granular soil is above the clay layer. So again, this would be the way you are able to calculate the downward force drag. Now, this is extra information. For now, you only need to know what the negative skin friction is, which is the negative downward drag due to a contraction of clay layer. Okay, so the formulas may not be necessary at this point. So for your case, just make sure you know what negative skin friction is. Okay, and then we have group efficiency. So I will put this in a very simple way. So in cases where now the load carrying capacity, a greater load carrying capacity is required more than the pile. We know we started from pad footing. Okay, from pad footing, So we started from pad footing and pad footing. Uh, so pad footing, if that's not sufficient, you can combine two pad footings, and we already learned how to design all this. You can combine two pad footing in whatever shape. They could be trapezoidal, could be ordinary at a rectangle, could be triangular. I'm yet to see that, but it's possible theoretically. Could be yeah. So while those things are possible in theory, but you also need to consider the constructability. So if a footing was triangular, how then would be, in theory is possible. Of course, with also in real life it's possible, but with some effort. So we are trying to avoid that because you don't need to make it unnecessarily difficult to construct, given that the other people are going to try to implement what you have. So the principle again is to make it easy, the ease of constructability. Whatever you design should be easy to be constructed, or it should not require so much effort to be able to construct. Okay, so now from pad footing to combined footing, raft footing, you can reinforce them with some beam. So those are shallow foundations. Then if that is not enough, you can go to raft or mat footing, where it's a whole pad. Okay, if that is not enough, and you had problems of settlement, then you go to piles. Okay, piles and piers, which now you should know how to deal with. But then if that is not enough, then you can have a group of piles. Okay, so if the loads are massive and the soil is not good enough, then probably you can uh, graduate from just a single pile to a group of piles. So very simply, I won't say a lot of stuff here. The notes are there for you to read, but here, simply put, is that if you have, so you have several piles, several of them together. Okay. The point is several of piles together. Of course, there are regulations of how the distance could be, and then you you join them with a pile cap. So this is a pile cap. So pile cap is what will make sure the load is transferred uniformly to all the piles. So this is a pile group. There are rules governing the how close you can put piles actually, because you can imagine if you have a pile there, then there is the region of influence. Okay, so if you put another pile too close, then the region of influence will interfere with each other. But that's not the point of this work. The point here is that, so I don't know, because I've run out of space, allow me to delete this. So the point here, in fact, is that so if we take a cross section, And say we have 1, 2, 3, 4, 5, 6, 7, 8, 9 piles. Okay. So this is the bird's eye view or in plan. So this is the pile. And we are talking about a pile group. So if the capacity of each pile, capacity of each pile is say 10,000, no, 1,000, let's say, kilonewtons. You'd theoretically say in theory, so theoretical capacity is how much of the piles drawn there is how much? Class rep? Capacity of the group. Class rep?
9 times 1000.
Which is how much?
9000.
Yes, this would be 9,000. But the reality is that capacity will not be 9,000. Anyone with an idea, will it be less or more?
Less.
Yes, good. Why? Hello? Class rep,
Yes.
why?
It does not have 100% efficiency.
Actual, why? That's what I'm asking you. Actual capacity is in fact less than 9,000, as you have correctly said. Because of the interference, I've just explained, Buana, before. Because of that interference, the actual capacity will be less than 9,000. So if, say, the actual capacity less than 9,000, and let's say it's is 7,000 kilonewtons. So the pile efficiency, pile efficiency is denoted by N group. Okay, is a group efficiency. I'm trying my best because it's quite difficult to write here. Efficiency. Because I'm using just mouse to write. And it would be now 7,000 over 9,000. So precisely, so that is usually a figure which is less than 1. If we had 100% efficiency, that value would be 1. So in a nutshell, that is what efficiency is, despite the fact that in your notes you have a lot of stories which you read. But this is the point. The point of all those stories, this is it. Any question, class rep?
I have no question.
Okay. Anyone else with a question? So the stories you read for yourself. So I already said this, and this is some way to help us design the piles. That if we can determine some length, some effective length and effective width, so LG and BD, this is a function of the number of piles, and also the dimension shown, the D, and incidentally, what does D stand for here? LG is N, N is the number of piles. I think it's described somewhere. D is okay, D is the diameter of the pile, okay? So this is why you need to come to class. So D, you can see D is not described here. And so D is pile diameter or pile dimension. And N1 times N2 is just the number of piles. So in this direction, how many? And in the direction, how many? So in this case, N1 equals N2, which is 3 piles, okay? Yeah, so it should be straightforward. And so these are some examples of group and the reinforcement. So here you can see the photo. Here we have 1, 2, 3, 4, and then the pile cap. So this is what is the pile cap. Because you want some rigid materials to be able to transfer the load uniformly to the piles. Okay, so we have a group of piles as you can see in the photo, and then this is the reinforcement for the pile cap. So also it's better to see some of this so that the idea is clearer. So a lot of stories there, which these ones you have to read, is based on basically what you have said. So we also try. Okay, no, don't need to worry. This is actually based on, you can see the FAV, which you have done. So here, what you need to do is just find an equivalent length, okay? An equivalent width, as we have said, because we first of all assume if there were piles along this length, block to block, that's the idea, but of course that's impossible, so there's some spacing in between. So then you find an effective length and effective width as has been shown. So that's the idea here. The idea of the skin friction is the same, and this is what you can see. So the average skin friction times the perimeter.
Excuse me, sir.
Yes,
Some of my classmates say you are not letting them in.
but they are late to class. They are late. The class was supposed to start at 10. So it's just if I am letting them in now, it's just a favor. So now I lost my track of thought. Actually, that's why sometimes I take some time, because now I was explaining and then I'm going to let them in. Now I don't know, what was I saying? What was I saying? Okay, so the same idea, but I'm saying now here you need to find an equivalent parameter. No, not parameter. Equivalent dimensions, equivalent length, equivalent width, and equivalent perimeter. So here you can see the same idea, but now we are talking about PG. That means the equivalent parameter of the group. So, so in this case, if we were to think about it, the equivalent parameter The equivalent parameter would be here now BG times LG times the length of the pile. Okay, so here, so let me just write that to elucidate the point. So here, for example, PG would be, it's unfortunate that I have told you what it is. Is it? No, that's not right. That would be 2 into, okay, you people should tell me what would be the equivalent perimeter in this arrangement. Hello? Hello? Class rep, appoint someone to answer that question. Yes?
Two into bracket LG
2 into
plus PG.
bracket?
BG
Yes?
LG. BG plus LG.
Is that all?
That is perimeter.
No, the pile is a 2D thing, Mwana. That's the perimeter in 2D. But this is 3D, so times?
Times L.
Yes. So 2L. So times L. So the same idea. So if you want, and then if you have FAV, then times PG times L, and that would be the capacity of the skin friction. Okay. Similarly, you can do the same for the capacity of bearing. So very fairly straightforward, like we have said. Okay, so a lot of stories there which you read. I think it should be clear, and then you can sum because you are dealing with a lot of piles. So then, in a nutshell, we are saying the pile, the efficiency is in fact the actual pile capacity over the theoretical value. If you are able if you're able to calculate or to mobilize if you're able to mobilize the strength of each, the capacity of each, fully mobilize the capacity of each pile, then the efficiency is the ratio of the actual capacity over the theoretical capacity. No need to worry about the formulas, the too much formulas. At least this one you need to know, the simple one. But in this case, your job is only to know what pile efficiency is, and you should be able to define what it is. That is the ratio of the actual capacity of the pile to the ratio of the maximum or the cumulative sum of the maximum theoretical value of the pile capacity. Were it possible to be able to mobilize the actual capacity, I mean the maximum capacity of each pile. So the example that I've given you, okay? So I think the example made it. Oh, actually, the reason why I make very simple explanation because the writing, a lot of stories is easy to confuse people. While my point here is to make sure I'm communicating very clearly so that you understand the point. So while you read the notes to bring more clarity, okay? So I have tried to make it very simple. so that you can understand. So these are details that are good for you depending on your capacity to absorb. Now, in this case, you only need enough knowledge so that you pass the exam. The first thing is you absorb enough to be able to pass the exams. If you can absorb above this, that can serve you in this field, well and good. But also you need to be aware, just in case you find something like this in future. So the if okay, there is also interesting here. If the center to center spacing D is large enough, actually the capacity, it's possible the efficiency can be greater than 1. That's very interesting. In this case, the piles will behave as individual piles. Okay, so here, so for a group that is, what did I do? So actually, in this case, these are individual piles. So that's not a group. When n is greater than 1, that's not a group of piles. Usually, for a group of piles, n is less than 1, as in practice. Okay, like I already said in a simple way. And so these are several ways of getting a group efficiency of friction piles. Okay. Actually, the pile group is implemented because of of uh, the skin friction rather than the end bearing. Okay, so please note this. So usually this is a skin friction thing. So usually these piles are skin friction piles rather than end bearing piles or point bearing piles. Okay, so these are several formulas from several jurisdictions. Okay, and some in engineering, as usual, we always, instead of, you can see the formulas are uh, complex, and for engineers we should not say they are complex because that's what we do, but our job is to make complex things easy for other people to be able to use. So we should not say that these formulas are complex. We should understand the formulas, then synthesize them in a simpler way for other people to be able to absorb. So we should understand the formulas, also understand the simple curve. So now, instead of all those complicated formulas, we have a nice a curve here, and because of the um because this is a frictional pile, basically these are friction piles basically, so the point bearing is usually ignored. So this is why you can see the curve is based on phi, which is a property of friction soils. So nicely, if depending on the arrangement that you have, you just need to know the diameter and the distance d, and based also on the phi, you can find group efficiency. So so you can see this is very nice for our use. So in the case of you, in your case now, as at undergraduate, probably I'll give you this chart and some dimensions, and you're asked to find the group efficiency from a curve like this, just to keep things simple for you for the level of an undergraduate. Okay, at other levels now, you need to interrogate these formulas and see whether they are making sense, whether you can improve them, whether you can get better results out of them. Okay, and so okay, maybe you don't need to know that. If you need more information, this for other, you can pursue in another additional degree. So for the purpose of this class, please make sure you understand what the pile efficiency is. You can explain that ratio, okay? And if there are any calculations involved, then you can be able to use this chart, which should not be an issue to you, provided you've been given D, the small d, I mean the capital D, and the small d and the phi. Okay, then you should be able to do some calculations based on the information provided. Okay. So there are several other equations. Okay, no, we're past that. Okay, so so two things we remember. So there are frictional piles, okay, and there are also end bearing or cohesion. So because in sand, so what we are dealing with here is group efficiency in sand and friction piles. Okay. No, it's still friction even in clay, but like we've said, clay and sand behave totally differently. So the pile capacity in clay, which is the same, nothing different from what we've talked about, but just the way we were treating, just the same way we were treating single piles. You can see these formulas are quite familiar. AP, 9CUP. This is quite familiar, should be quite familiar to you. Okay. So for a pile group, things may be, what will make a difference is that we may have different cohesions. That's all. But the idea of the length of the group, the width of the group is more or less what we've talked about. Okay. So the only difference would be this, we might have different cohesions along the because we have several different layers of different soils. Okay, so that's it, that's all. So you find the equivalent length, which we already know how to determine, equivalent width, all right, and representative, which you need to sum. Actually, that's the reason for the sum here. Okay, alpha. So alpha, all these things are the same. Now P is the equivalent perimeter because you're talking about um, um, uh, a pile group, okay, which we now know how to find. So the sum simply implies that you find alpha and all that and sum for the first length because this CU is different, then sum for the second length because this CU is different, then for the third length, and you add the three. So that's the meaning of the sum. Otherwise, this principle is derived from uh, the the ones we already spoken about individual piles. So the same principle, once you understand and then you apply here, considering the fact that this is a group. So remember the pile group, I said 2 Lg times B. So that's something that should be clear to you. So the only difference here is Cu maybe Cu may be differing, and all this can be found from experimental work or from site investigations. Okay, so that's it. And if you want to calculate the bearing capacity, so the point bearing is the same idea. The point bearing, uh, the same idea for individual piles, but now considering a group. So the area now would be Lg times Bg and Cu. So but here now you have to use the bearing of the bearing of the foundation soil, or the soil at the point or at the tip of the pile. So please note, for sand, the friction contribution to the bearing capacity is much more than the end bearing. In any case, the C for sand is 0. So this is why in these capacities for those in sand, we never said anything about the tip bearing, the point bearing. Okay, if you remember, Now here we talk about the skin friction, which you can calculate from here, and also the capacity of the point bearing, because in saturated sand especially, yes, cohesion, the phi actually there is 0, and then the phi is 0. The strength is contributed to by the cohesion, and if you remember very well, we can find a bearing capacity factor NC based on phi equals 0. All right. So then you can add the two. So summation of the ultimate bearing capacity is the addition from the capacity of the skin friction, which we established here. Where is that? Okay, here, the capacity here. Okay. So that is, you can see that here. So this is from the skin friction. So the skin resistance there, and then the capacity at the tip. So goes closest what we said, that in fact so this is actually strengthening what we said. But remember, this is the ultimate pile capacity. So strengthens what we said, that the capacity, ultimate capacity of the pile equals the capacity from the skin friction plus the capacity from the point bearing. Call it QB. So here, this is QS, and this is QB. But remember, this is the ultimate. So for the one to be used in practice, you need to apply a factor of safety. But at least this is how to determine the bearing capacity. Okay. And okay, there's a procedure there. You read a lot of stories there for you, but you compare. So this is how to get. Okay, there's a procedure there. You read the details for yourself, but the point here, make sure you understand what is to be done, and you can get NC from a ratio of L over BG. So this is a curve for group of piles. So this is also another love that we have in engineering. We love to, as much as we love the formulas, which some of you might think are complicated, but in fact they are not, if you understand what is happening. And over and above that, we like curves that even simplify the formulas, so that those of you will think that those ones are the formulas are difficult. Then when you have a curve, then you have no excuse, because it's just about reading what you can read from the curve. So this is how you can get NC for a group pile based on the dimensions. Okay. And at your own time, you can try to follow the formula, relate with that of single piles, and see what is happening there. And also look for questions that you're able to do. If you want, I can send you a list of questions that you can try at your free time. And this is not moving. So again, so we already talked about capacity. So if you think about this from the perspective of piles, we talked about the pile, the capacity in sand, capacity in clay, and everything, the settlement in piles. So again, we are going to do the same thing with the group. We've talked about the group efficiency, the capacity of skin friction, the capacity of the group of piles, the issue with pile efficiency. Now we need to talk briefly about the settlement of a group of piles. So in general, the settlement of a group pile under similar working load per pile increase with width No, so I'm averse to a lot of stories. So please, this is the formula. You can see the formula for determining the group settlement is just based on the length, on the width, the dimension, and the diameter of the group. Okay, and SE is the settlement of an individual pile. So that's how you can be able to estimate the settlement, and you can convert this in inches as well. Okay, no, sorry, this is a different author. So this first one was developed by Vesic. Okay, so these are just formulas whose meanings you know, and you should be able to calculate given any of the conditions. So these are such a simple formula you should be able to remember. So you will not in the exam you don't expect this to be given to you. Um, and also someone else, Meyerhoff, suggested, but note that Meyerhoff's value is in inches. Okay. And also these values in tons. Apparently, the US people insist that they might be different from others. So while the rest of the world have their units, the US have their own, which is fine. You should just know how to convert. So this is the conversion. If you conversion for Mayhoff, if you have in millimeters, the initial one is in inches. This is now in millimeters. The meaning of all that is in the is defined there for you. So okay, so you can relate this to the like I said, always it's always a good idea for practice to be able to relate all this. We are interested in the capacity, we are interested in the settlement. If you're able to do an experiment, do the N60, then we can directly relate the N60 value to a settlement. That would be very nice for us. So this is the idea actually. So here again, relating the settlement of a group of piles with the SPT, standard penetration test, and 60 value. And again here we can also relate with the cone penetration. That would be useful for us. And then finally, this is something about settlement in consolidation settlement in clay. But if you look at this formula keenly, this is nothing more than the consolidation settlement, which if you are different students, you would say I didn't teach you, but I already taught you how to do this. The only difference here is that the increments in the load increments. Now someone is just joining class when I'm in the last slide. The load increments here are from the group of piles. So here you treat this the pile, the dimension, as if it's one as if you would use, for example, as if you would treat, for example, one rigid foundation. So you reduce this to uh, the group to a section similar to that of a shallow foundation. Okay, so then this is what you can see here. And then the increment in load is basically the related to the pile load, and as the from the formula that you can see. And Zi, of course, is the depth, is the depth upon which you are interested in. So so the depth is your area of interest basically. So here, if you are interested in the depth there, so you will have to know what this value is. Okay, so that's it. If it's 10 or 20. So that's it. So once you know what that's the depth is, you know what the group length is, the group width is, the group capacity, then you have no issue. All these things, the coefficient coefficient of what consolidation, you know now, and height is based on the height of clay, and sigma naught. These are the initial in situ stresses before you constructed the pipe. So basically, this thing you know, and the CC, whether you are going to use CC. So in this formula, actually, I made it very simple, assuming we are talking about consolidation settlement. But in fact, it's possible you can also use the other one was called what? We have coefficient of consolidation. Let me see now those who remember. You can also use coefficient of this curve. Anyone who remembers? Or you people just read for the exams. Once it's over, you're done. This curve here. So because I remember, I'm the one who taught, so there's no excuse for you. You have no excuse. So we have log sigma. Is it log sigma? Yeah, and E, yes. Log sigma and E. And we have this nice curve here, consolidation curve, which sometimes you can do unloading, reloading. And that's the curve nonetheless. And then if you decide, so if you want to find the pre-consolidation stress, you draw this. Okay, this is the simplest way to do it. And this is sigma P. And you can have this, the coefficient here, and which is should be parallel to that part. And you also have the gradient here, and this is the CC. You can use CC or which one? The gradient there is called coefficient of class rep. I will ask you in the you are the default person. If you can't answer, you appoint someone to do it. Hello? Hello? Class rep. Hello?
Yes, sir.
Yes. Appoint someone to answer the question. Hello? Hello? Or you answer it yourself. We said we can have over consolidated clay, normally consolidated clay. So silence means people are still referring or they're not interested or what? Masi Ndanu. Masi. Masi
Yes.
Ndanu.
Yes.
Are you able to answer the question?
No.
Why? And others are joining class now. please check this, the issue of over consolidation and normally consolidated soil. We learned that. So here you can also use, depending on the kind of soil. So this formula is applicable for normally consolidated clay. Of course, there's more information than that. This is suitable for normally consolidated clay, and the normally consolidated clay remains normally consolidated even with the application of delta sigma 1. Okay. Now, if the soil is over consolidated and transfers to normally consolidated clay, then you have to have this plus the same formula, but in this case, we'll be having coefficient of swelling. Okay. If it is over consolidated and remains over consolidated after addition of this, then either you use only this formula, but this is CE. Okay, so you should remember that. So this is the idea. So the primary idea of calculating consolidation settlement, you already know. The only difference is the now this is a group of piles. So how to determine the incremental increase in stress is different based on the group of pile and the additional dimension. So nothing new except now the dimension of the grouping of the pile. Okay, so if you don't know, you need to review the notes we just covered in the first course. So I'm not happy by there. I need to tell you, not happy with the participation. You need to participate, but that's the only way learning can happen. Some of you are just joining class just now when I'm on the last slide. Again, when you fail, the lecturer. So, but it's up to you. Like I say, you're the one in school. I do my job. I teach you. I finish the syllabus. I set the exam as best as I can. You choose how you learn. Whether you pass, if you pass, you'll pass. If you fail, you fail. But it's my hope that everyone should be able to pass. I don't see any reason why students fail. In any case, the exams we set is really dumbed down. If you can appreciate, because you can see, for example, the group of piles, the best, the only thing we can set, because we understand the level, the setting has to be put to the level. You can see the formulas there, but for your level, what we can set, if at all there's any calculation, is this curve, which if given the D, actually this one you don't even need anyone to teach you. If this curve is given you and no one has explained anything to you, somehow you should be able to figure this out. Okay, and for the skin friction, you only need to know what that is without the calculation. So the description, how you describe based on your own understanding, of course, based on what we've talked about. So I really don't understand why students often fail. Now you can see this one, the settlement. Some of you, I know you don't remember, that's why the pin drop silence. But this is something you already talked about, the consolidation settlement. So this is nothing new, except we've added the dimension of the pile. So actually, if you think about this, actually, even from the idea of shallow foundations, you get it, because shallow foundations always have a dimension like that, and there's a formula of how to get the increment in stress due to at a point inside the soil due to some additional stresses. This is something you should have. I think you may have covered, or no may you should have covered. There are certain formulas of doing this. Of if you add a load, on the surface, then that load So let me try to explain to you. If maybe if that can help you. There's a way we can. So if you, for example, this is the surface, and you've added a load or stress Q here. So those stress will increase in terms of bulbs. I think this is something you should. Class rep, have you done something like this?
Yes.
Yes. So that this would be 0.9 Q, 0.8, and the point is the influence of that load is reducing the deeper you go inside the soil in terms of bulbs. Okay, maybe I've not done it very well. Let me try again. Q, so like this, and they're usually bulbs of. But the point is, it down here the influence of that load is very, and there are certain formulas of how to do that. So nothing new. If you relate exactly what you've done, then very should be very clear. Okay. So that's the end of this place with piles and the group. So there is another guy. I like his. You're supposed to know about caissons. Is called Orwell Foundation. So there's a guy. Okay, maybe not today. So you have the notes already, and so we just call the attendance, and that's it. Unless there's a question. Question silence means everyone is fine. Okay, so we